Log on, tune in, find out. Another good idea from Cambridge.
So this last session of the morning is something which is a bit new for the DEMA conference. Rather than having a set of 30-minute presentations, we're going to have a panel discussion on future directions for the design of experiments. So we have a panel of 5 distinguished experts in the area of design of experiments who we selected because we thought they might have different views amongst them about where the design we're
Can't imagine why.
So what we'll do is each of these 5 will talk for around 5 minutes, giving their view of where they see the subject going, and then discussion will open out to the audience, and we hope lots of other people will give lots of other different opinions. So we'll see how it goes. But the first speaker is Anthony Atkinson, who is going to kick off.
Super. Yes, thank you very much. Okay, off we go. I'm supposed to have 2 slides. I'm rather more than that. That's 1. That's 2. Okay. All right. So I want to start off talking a bit about algorithmic design. This is what I personally think of as Pete and Brad's awfully big idea. This is a book, a recently published book by Peter Hoos and Brad Jones. It's called Optimal Design of Experiments, a Case Study Approach. Some of it comes from their consulting, some of it comes from working around published case study papers. And there are little stories, you know. Brad in disgust slings his laptop on the back seat of the Chevrolet and drives down the New Jersey Parkway. This kind of thing. Okay, but the statistics. This is perhaps I exaggerate. The statistics. The statistics is serious. One of the authors is really called Peter, of course. Newton Mass, where Peter tells me he has never been. This is one of those stories. Dr. Shu I think is fictitious and so on. However, the rest is all real. Wants to divide the 32 trials of a 2 to the 6 minus 1 fractional factorial design into 4 blocks of 8. So we've had some of this in the meeting so far. Unfortunately, when one does this, some 2-factor interactions are confounded with blocks, and partial changing of the block generator doesn't solve the problem. You don't have to confound everything with blocks, the same blocks and so on. However, what they do is to calculate a d-optimal design which is almost orthogonal so that everything of interest can be well estimated. This is an example. There's a lot of work on properties of projections of fractions of fractional factorials and so on. Instead of that, this is a calculation approach which may give at least complementary results. Of course, the problem here is, good heavens, 5 minutes are up already. Why 32 trials and why blocks of 8? Well, presumably Dr. Zhu or one of his colleagues have been reading books on the design of experiments. So is it in this case, might actually want to have blocks of different sizes if you've got different size sacks of the raw materials and so on. So that's one thing. This is something to do with medical trials. This has come up a little bit not this week really so much, but in previous weeks. Well, Nancy Flournoy's talk, I suppose, dose response. There is quite a lot of literature, a huge amount of literature, of increasing and decreasing doses. The properties of convergence of some of these designs are not particularly well understood or are rather ignored, although coming perhaps from the control literature, Luc Pranzato gave some talks on the properties of designs, which kind of designs converge and which don't. So it'd be useful, I think, for people to take the results from 2 and apply them to 1 and wonder whether in fact convergence matters at all if you've only got 30 patients that you're trying to deal with. Okay, this is something that Valery Fedorov said, practical designs. This is an example, in fact, that I gave in a talk here. So a traditional design has 120 trials, different combinations of design points. The non-linear model has 3 parameters. So the design has 3 support points, and the rich design then has a d-efficiency of 18% or so, should not be used. But I don't think anybody would recommend that they should use a 3-point design for this model. Because, for example, it doesn't allow for model checking. What is some systematic way of coming up with a slightly richer design? 5 points, but what kind of criterion, what kind of ideas might be used? Okay, so these I think are probably comments on strategy. Let's get this right. We're on tactics rather than strategy. Here is something perhaps a bit more strategic. When Valery Fedorov was talking, he said all you have to do really is to find the information matrix, and then you have an algorithm and you find MXI star. That's the information matrix for the optimum design. So here's my thing. There is more to the design of experiments and consideration of the properties of MXI star, isn't there? And then the question, of course, is what? And then people can discuss that. Thank you all very much. Oh yes, I'll do that. Oh dear, now I've spilled the water and everybody can hear me doing that because I haven't turned the microphone on.
That's what I want.
You better turn it off.
You have to take it out of your pocket, yeah?
I think I have to go away one time, just get some napkins on.
If it's on my notes.
Don't say anything interesting for lots of minutes.
Okay, so our second contributor is John Stufken.
Okay, thank you, Steve. I have strayed a little bit from my assignment. I'm not going to talk about really research directions, but I'm going to talk more about research challenges a little bit. I think for several reasons. It's not because the directions are not important, but if you have seen some of the talks here, if you've listened to some of the talks, and if you haven't, you can go to the website of the Institute. You can still see the talks that you might be interested in. Then there are an enormous amount of ideas there. And if there are young people who are interested in working in design, who haven't quite decided whether they want to work in design, this is a great time to start working in design because there are so many opportunities, there are so many problems available. But at the same time, I think we have some challenges, and so I want to pose some questions that have to do with those challenges. And maybe other people have different views about this, don't see them as challenges. I would be interested to hear about that. So there are virtually unlimited opportunities, as I said, and if this particular conference as well as the previous workshops, if you look at the talks there on engineering, biological scientists, healthcare, geological scientists, business, there are people that are shouting to people in design and say, hey, we need your help. I mean, come and work with us. And if we're not going to do that, then of course they're going to come up with solutions themselves. They're going to do something themselves. We should be involved in all of those activities, and some of the people here are involved in those activities already. What's going to happen? If you look at those talks, you can get some idea about research directions for the next 2 or 3 years. What's going to happen 10 years from now? What are we doing 10 years from now? I really don't have a clue. So I'm not going to talk about that. So I will sidestep the question of research directions. And we'll try to focus on broader challenges for design of experiments. And maybe then the first question is, well, what is design of experiments? Or perhaps better, what is statistics? Because I think the answers to that question are somewhat similar to the answers to what design of experiments is. And I'm going to show you this in a picture, and you may not quite recognize it, that this is the profession that you're involved in. But keep that picture of the wheel with you. And I'll try to explain why this is somewhat relevant. So there was a workshop at the National Science Foundation back in 2002 that addressed precisely this question of what is statistics. This was a workshop with 50 participants, approximately 50 participants, invited participants, mostly from the United States, mostly focusing on funding for statistics. But in trying to make the case as to why statistics needs more funding, of course you have to talk about what does statistics do? What is the impact of statistics? And so there was a lot of discussion there about the interaction between statistics and other disciplines, and how we should try to do a better job of that. So mostly people from the US, but some people from abroad. It resulted in an 80-plus page report to the National Science Foundation, edited by Bruce Lindsay, John Kettering, and David Sigmund. And if you haven't read this article, then I recommend that you have a look at that. So an abridged version of that report appeared in Statistical Science. It's a report on the future of statistics. And in a very simplified way, the conclusion was there are really three parts to statistics. One is the core, where fundamental research is being done. In addition to that, we have collaborative research, where we interact with all of the other sciences. And then we have, I don't know whether maybe this word has a somewhat negative connotation, but I don't mean it in a negative way. We have the straddlers who move back and forth between the core, who make important contributions to the core, but who are also involved in collaborative research opportunities. So with those three groups of people, if you have this in mind, well, that's exactly where the wheel comes from, right? I mean, the core of this discipline, that's the hub of the wheel. And then the other sciences, they're all on the rim of the wheel. That's where these collaborations take place. And the spokes of the wheel, well, those are the lines of communication that exist between, and that must exist between the core and the applied research that's being done on the rim, the collaborative research that happens there. And so that picture has statistics as a very central science within the sciences. And I think you can make an argument that that's indeed the case. And if you want to make an argument that statistics needs more funding, I think you have to make an argument of that type, that statistics is indeed very central to the scientific enterprise. And each of the three components, obviously, the hub, the core research, as well as the collaborative research, as well as the interaction between the people in the core and the people on the rim, they're very important parts for the success of the research enterprise of statistics. And I think you can apply this as well to design of experiments. I mean, it's not just a picture that applies to statistics. It applies to the whole of design of experiments. Now, if you buy this simplified picture, and you may not, then I think a few things are clear. And maybe I'm talking from my experience in the United States, and it's quite possible that experience in Europe and elsewhere are different. But you have to come to the conclusion that there are enormous opportunities for design of experiments. I mean, there's so much activity on the rim. There are so many areas where we're actually not very much involved yet, where there are opportunities to get more involved. Data is collected everywhere, huge amounts of times. There are problems where more complicated models are needed, need to be dealt with for maybe optimal design purposes or design selection purposes. And it also shows that we need contributions from people with very different talents. Somebody who's good at the rim is not necessarily somebody who's good in the core, and vice versa. So we need people with mathematical skills, we need people with computational skills, we need people with very different skills. But I think we also face many challenges, and I've tried to address that through some questions without giving much of answers, but I would be interested to hear what other people think about it. So the first is, do we have the human infrastructure for research activities in the core and at the rim? I mean, do we have enough people in our discipline? Most of the time when I go to meetings, I mean, I see pretty much the same group of people, and yeah, there's some new people coming into the discipline, but are there really enough people coming into the discipline? And I know there are some people who are fabulously successful in attracting people to come to design of experiments, but it seems that there are maybe too few people who are successful at that. Do we attract some of the brightest minds in statistics to design? And maybe if you look outside of statistics, maybe brightest minds in mathematics and the sciences, do we attract them to come to design of experiments? And if the answer is no, then why not? Is there something that we can do to improve that? Can we make the area perhaps more attractive in some ways? Do we have enough people who speak the language of scientists in other fields? And if the answer there is no, then is there something we can do about that? Maybe in terms of our training, maybe we need more flexibility in our training and have people who are interested in interacting with other scientists, have a program where they can already during the training do that more than is currently the case. Are we sufficiently successful in collaborative research teams? And again, I know there's some people who are extremely successful at that, but as a discipline, is there enough going on? I mean, we have to work on problems that people care about. Because if you just work on problems that we care about, then we're not going to grow very much. What is the reputation that we have within the field of statistics? Probably not all that good. At least again from the U.S. perspective. If you look at the universities in the United States, there are many top universities where you won't find any people working in design of experiments. So. Computing, knowledge of algorithms, are we really at the forefront there, or is there something that we can do better? And maybe there too, you can ask about the training. Do we need better training for that aspect? This is probably something that we cannot do very much about, and maybe this related to some of the earlier questions, but do we have enough flag carriers? Because the success of a discipline has a lot to do with big name and people who have vision, stature, and excellence. If you have a Fisher, or maybe you have some other names that one could mention, but that can really energize an area. And so then, again, I've not really given many answers. I've asked questions, and I'm really interested to hear what other people think about those questions. But then the end, the question is, what changes are needed, if any, if design of experiments take advantage of the available opportunities that unquestionably exist to be a vibrant and attractive and influential research area 10 years from now. And I'll leave it at that. Thank you. Yes.
PowerPoint and the PDF? Is it PowerPoint?
Just the PowerPoint's good.
So thirdly is Bob Wilkins.
Thanks. I guess to continue John's talk, I guess I'm a straddler. So, and I spend actually most of my time on the rim. And so I'm, I guess, a full-time practitioner and a part-time researcher. I work at a chemical company, Lubrizol. And we have a lot of interesting opportunities for design, and I think our research ideas come out of the things we observe, the needs we want, both in actually DOE and in modeling and other areas. So, and we're not opposed to stealing other people's ideas, meaning working with people that are in the core to help us. So I'm going to start really fast and go through just sort of motivate one area of research which I think is very interesting. And that's by telling you a little bit about what we do. And so we're a chemical company, and we put together these complex chemical formulations. And the idea is to come up with models that actually predict future formulations and things. So what do we come up with? We want it to be able to interpolate and extrapolate to a reasonable amount. And so we have to design using the science of the field, and the science of the field are chemical factors that are actually functions of the ingredients you put in a chemical formulation. So what does all that mean? Well, I don't know if I convinced you, but actually what it turns out is that it actually ends up in a very constrained design space because of that relationship with the chemical factors. And because it's very complex formulations, what happens is we have a very large number of variables. So we're in a constrained space with a large P. We do want these things, whatever we do, to predict. But by the way, time is of the essence, and money is of the essence, and being first is so important. So N small. Some of our tests do cost like $100,000, so that also helps with N small, but $100,000 it runs for like a month or something, the test. So we have to be quick. So I've sort of motivated the case for, I guess, super saturated designs or screening designs, but I've actually gone to a place that no one goes and says, well, screening designs can't be used for prediction, but actually we do use them for prediction. And they actually work, for the most part. But there's lots of issues. So I'm going to break it down into 3 pieces here. On the design piece, there's been a lot of work in this area. And I think there's a lot of computational issues still. And I'm not an expert, and I don't know, there's a lot of people talking about algorithms and things, but we're in a constrained space. And so given a criterion, finding that optimal design, that best design, I think it's still an open-ended question in good research. Going to the criterion, I think instead of going after like a model and finding the best design for this model, because we don't really know what the model is, what you want to do is come up with the best design across a group of models. And so that's sort of, you start thinking Bayesian here, and since I was trained at Carnegie Mellon, I guess I'm a Bayesian. So you start averaging over models and start looking at that type of work. But by the way, it's real data we're looking at, and so you're going to lose data possibly. So you actually have to incorporate in the possibility of losing data. And by the way, sometimes you lose data and you don't even know it, and that's called an outlier. And so you have to incorporate that. And so you can do that and incorporate it into your criterion. It does make the computation a little bit harder, and how you do that I think is a good research area. But I think if we go to the final piece, I think in the end, what's a determinant? I don't know. And what's a correlation? I don't know. What I really want to know is what factors are important. And so a lot of times what we do now is we simulate, and I won't go into the details, but we simulate under reasonable modeling conditions, can we pick out the variables? And so you do that after we come up with the design to see how good it is. Obviously, maybe what you want to do is come up with the right sample size and the right design to get you, so you're pretty highly probable that you can estimate, or you can pick out the important factors. So it's working sort of the optimization in another angle. And it sounds very hard, so that's why it should be research. I'll go quickly through the analysis. I think the analysis of supersaturated designs has come a long way in the last 5 years. I think the design aspects were way ahead. The analysis caught up, and it actually stole ideas from data mining. That's what we did. So we did a lot of Bayesian model averaging. There's other techniques. I think they work pretty good. But as you get into sort of nonlinear functions, I think things like, I don't like Taylor series. I like radio basis functions, for example, with Jeff Wu. I sort of like things that interpolate, extrapolate well. And the other thing we come across a lot is even in normal data, the mean function is often S-shaped. So you have this sort of linear or simple model moving along in S-shaped. That sort of creates a whole area of design, right? How do you design for something like that? And then the analysis too. So I'm almost done. I threw in communicating because actually in the end of the day you actually have to hopefully communicate, and that's where all the value comes. And I think Jump has the nice profiler, which people, by the way, love. I mean, and you put it, you give them the profile and they can play with it. We do a lot of web services stuff, but this isn't really mathematical, but it is sort of an interesting area. I think it's it's kind of like the graphics area of statistics. Is how do you convey the information, particularly when you start getting big models, lots of variables and things. So I'm going to skip the knowledge, although that's a very interesting area. And I guess the last thing is, different types of responses. I talked about that sort of S-shaped thing, but functional data is really big right now. And, yesterday I had a good talk on that and talked about how creating that vector. But I think when you create that vector from your function, how do you relate that to the design variables? And I don't think you should just relate it in a very simple sense, because I think it's actually on the wrong scale often, and so in order to have a simple model, and you want a simple model, you'll never be able to interpolate or extrapolate. You need to think hard about how you relate that vector to your design variables. And that's it.
So the fourth, if I've counted correctly, is David Stein.
Thank you, Steve. Steve told me I was going to be fourth, so I guess we're on the right count here. I also had him guarantee at the start that this is a randomized order of speakers. Okay. A few words on future directions, although I'm not actually going to say that much about future directions. So where are we headed? And the only way to start here is with one of my favorite Yogi Berra quotes. Prediction is hard, especially about the future. Having tried to do this once with experimental design and failed miserably, I'm going to be a bit circumspect. And I decided that rather than direct initially my comments about what I see as some of the areas ahead of us in the future, I thought, having spent the last good part of the last 4 years editing Technometrics, which has been a primary venue for publishing research in experimental design, I thought it might be worthwhile to take at least a little bit of a look at where we as a research community have been. And keep in mind that Technometrics is a bit of a niche journal. I mean, it's certainly one of the major journals in the field. It's jointly owned by the American Statistical Association and the American Society for Quality. It's been a main venue for publishing work in experimental design, but with more of a focus toward engineering and the physical sciences. So a lot of the things that have gone on, for example, on the bio side, have not really made their way into technometrics. So keep in mind, this is a little bit of a biased picture. But again, I thought it might be interesting to see what we have been doing, and that can be useful, I think, in matching against some of the things that we've heard about what we should be doing and where we should be going. So this is a summary of papers that were submitted, as opposed to being published, from 2007 to 2011. During 2007 to 2009, that's the area that I'll primarily focus on, because those are the papers that actually, if you sent them in, they came in to me. There were a total of 534 submissions to the journal, and of these, 126 were related to the design and/or analysis of experiments. So certainly a major contribution. And this is just a breakdown, my breakdown, of how these papers divided up into rough areas. Computer experiments is the most popular area, and that's certainly an area that's it's become a major research area, I think, for people working in design. You certainly heard, of course, a lot of focus in Jeff's talk yesterday, as well as, of course, the workshop that will be held here next week, which is entirely on design and analysis of computer experiments. Most of the papers on analysis, as opposed to more of a focus on analysis as opposed to design. But again, this is certainly an area where a lot of us have been devoting attention, and it's clearly in part an area where technometrics, again, in this sort of biased view, has really taken up a strong role in publishing papers. Factorial experiments continue to be a very popular topic. Some of the papers are more directed toward analysis issues, but there are quite a few papers coming in on the design of factorial experiments, and I broke down just a few of these into some more specific areas. So for example, if you look at blocking, orthogonal arrays, run order, we haven't been doing much work there, at least not submitting it to technometrics. Combinatorial construction is really things that go into very, very detailed algorithms on building large, complex factorials. Split plot experiments, response surface methods have been popular areas. Screening. Biotech, I saw very little. Mixture experiments, which was once a very popular topic, is not very strongly on the map these days. Generalized linear models and nonlinear models also has not attracted a lot of attention during those years. Robust design in the sense of Taguchi, and some other stragglers, a couple papers in reliability, a couple related to design for measurement systems. So these are some of the areas where we've been devoting effort. The results for 2010 through 2011, July 2011, which I've gotten from Hugh Chipman, who's the current editor, are fairly similar. Hugh took a somewhat different tack in the way he organized the things that have been submitted, rather than focusing more on the topic area in the sense that I did. He divided them up in terms of papers on, again, many on computer experiments, although mostly on analysis, papers on optimal design, on analysis, papers that were application oriented, and papers focused on split plots and blocking. So this gives, I think, it's at least a little bit of a view of some of where we have been. As far as where we're going to go, this I decided to put off the record, although I guess since I'm going to be filmed on this, it's not really off the record anyway. And I'm not going to say a great deal because much has already been said. But I think if I had to venture a prediction as to where the most interesting things are going to come from, I think there are two things that are likely to drive those more than anything else, and those are applications and computation. And those are, I think, have driven a lot of the work that we've done throughout the history of experimental design. I think that's going to continue to be the case. We certainly need to foster the sort of collaborations that John was talking about, because those collaborations are going to be, I think, main sources of interesting new developments. And I'm just going to mention three areas that I think simply because they haven't come up yet, and where at least I've run into interesting problems recently. One is experiments on the web. I haven't heard anyone talk about running experiments on the web, and like there's a number of interesting questions that come up with these kind of experiments, and this is where we're living in these days. Second area, and this was a topic of an earlier workshop, which unfortunately I was not able to attend here, is sensor networks. And sensor networks are becoming much more common in all kinds of fields, for all varieties of sensor networks, and there are some interesting and challenging problems that come up in those areas. And the third area, and this one I don't know if it's a flash in the pan or if it's going to be a panacea that's going to create a lot of interesting research problems as well as a lot of interesting work for statisticians, is quality by design, which is sort of a buzzword in the pharma industry these days. Been adopted by the FDA as sort of an official policy to push, as well as by the European regulatory networks, with a heavy emphasis on use of experimental design in the development of new pharmaceuticals, as well as in the production processes and the sort of conditions that are authorized for producing pharmaceuticals. And again, I think part of the reason I said it is simply because I haven't heard it mentioned here yet, and that in some ways kind of surprises me. So those are just a few areas in addition to those that we've already heard about.
Okay, so to finish off, we have Rosemary Bailey.
Well, I know even less about this than the other people who've talked in terms of knowing about the future. So I'm going to just try and pick up some interesting aspects of what I think we have to be alert to in design of experiments. And you'll actually find that some of my points agree quite well with some things other people have already said. So first of all, just an example that interests me quite a lot at the moment is what we do in incomplete block designs. We know very well that if you have a design without blocks, what you should do is try and make all the replications as equal as possible if you want to minimize the variance of the pairwise estimates. And so quite a lot of us have been using block designs in all sorts of applications, and the criteria we've tended to use, we know we want to go to something that has low variance, and we've tended to search amongst things that have replications equal or almost equal, and we've tried to go for things that approximate to balanced incomplete block designs. And then there was this great shock 10 years or so ago when people suddenly started, in the context of genomics and microarrays, looking at blocks of size 2, and they were being very stingy with their experimental material, only allowing replication 2. And suddenly it was found that actually the lowest pairwise variance was obtained if you have a design in which almost all of the treatments are directly compared to a control, rather than getting equal replication. And so now some people are saying, oh, that's just a problem with block size 2, it couldn't happen for larger block size. Now, this program here has already been going on for several weeks, and we actually don't know the answer to that. From some explorations I've done, I think that if the average replication is very low, it's looking as if on the whole, you're going to have to go to a design that compares everything with control if you want low average variance, even if you're not interested in the control. But that's against all our instincts of what we do from thinking that replications should be equal. I don't know how to prove this at the moment, but some of my colleagues at Queen Mary, Mark Walters, came and gave us a talk here a few weeks ago. He knows lots of stuff that I don't know, or asymptotic combinatorics. And I think this may be where we do actually have to talk to really pure mathematicians, because they've got the mathematics to find the answer. So it's something about, if we're looking at low replication and large numbers of treatments, should we still keep to our heuristic of starting off with imagining we need replications equal, or should we also, as a matter of course, be looking at some more of these designs that compare everything with a control, using that as a benchmark and seeing what to do. So that's something where I think computer search alone isn't going to give us the answer. We need some real hard mathematics to help us. A second question, it's how we keep up with what is happening. I liked John's metaphor very much about having people in the hub and people on the rim, and we can't all be in all of the spokes. So I think it's very important that I go to the pub with biologists, for example. Those are the people I talk to, and other people talk to medics, other people talk to engineers. And so I do talk to the people who were involved in the whole microarray thing, and I know some people in the audience here who have actually closer relationships with the people doing all of that. And when two-color microarrays were introduced, these were biologists who didn't actually have a history of working with statisticians. Unlike people who are out planting things in the field, who know they're not allowed to go and do that until their design's been signed off by a statistician, you're doing something here in the corner of the lab, you don't know anything about statistics, you just get on with it. But because of that, you have no idea of what words you might look up. So you do, what's a two-color microarray? There are two colors, and that's crossed with several different arrays. If you're a design of experiments person, you think, well, that's a row column design. And there's more complications on that because there's all the different genes you put in the spots. But the basic design problem is something, a row column design with lots of columns and two rows. Well, computing power was quite good, and so people in the bioinformatics community, or even the biologists themselves, did computer searches to find the designs. Then some statisticians got involved and said, no, here's some theory, we can show you what the designs are. So we now talk to the people who are actually doing the genomics, and they say, oh, well, stuff that, we don't use two-color microarrays anymore, we use Affymetrix chips. Well, actually, that's not quite true because not everybody can afford them. But, you know, there was a point when someone said to me, please will you write a chapter on design for this general book I'm editing, and I said, no, I don't think I'd better because it's just not up to date with what people are doing. The technology changes. And it's not only that it changes, with some of the newer chips that are being introduced, there's statistical software built in. I say statistical in inverted commas. We are told that it is statistical, but we don't know quite exactly what it's doing. So I think there are huge challenges in actually keeping up with the sort of experiments that are being done. We can't just rest on this sort of design, that sort of design. There need to be enough of us talking to people who are doing experiments to keep up with it and to be able to work out what are not necessarily the best, because you have to do these things quickly, but at least to be able to have good design principles and help do the best thing for what they're about. I think this is the major new challenge. So then another more, well, this is particular but it's general at the same time, and this is coming back to the sort of stuff that Chris Bryan was talking about yesterday. We're quite used to the idea of experiments where we've got some experimental units and here we've got some treatments, and we've got to think about how to put those treatments on those units. The sort of thing that Chris was talking about is where you have more than one phase, and you can tell my background is in agriculture because my examples are almost all like that. So you think about something where you grow something in the field, and then you might take grapes and turn them into wine and have people taste them, or you take other samples from your crop and you do various things in the lab, and there might be further replication at that stage. And I think to even think about this clearly, we need to think about all the separate phases. What are our treatments? Are they quantitative or qualitative? Factorial or not? Is there a control? Think about the plots in the field. Do they come in blocks, or are we thinking about some sort of spatial correlation structure? then think further about the set of units in the lab phase or the tasting phase. And I don't think you can really think about the design until you've thought about all of those. But now we're going to have a design for how we put treatments on the plots, another design for how we take the stuff from the plots and use it in the lab. And you've got to think about the relation of those designs to each other for what is good overall. And I don't think there's been enough of that, because I think there are a lot of experiments that really do come in 2 or more phases and it hasn't been made explicit. Well, this slide I'm probably really just going to show my ignorance. We've heard quite a lot about optimal design, and I admit I don't know a lot about the criteria, as has probably been obvious from some of my questions, but I don't know whether we've actually got the right measures of optimality. Sometimes we're doing an experiment to actually choose amongst several models, and they might simply be nested one within another, or they might not be nested. Now, what I think is, in the sort of experiments I do, I draw a Hasse diagram for the family of models that we're considering fitting, and what we actually do is we go down until we can find the simplest model that's consistent with the data, and we estimate the parameters of that model. So what's our optimality criterion? Is it for choosing the model, or is it for estimating the parameters of that model once we've chosen it? So for example, if we have 2 factors in a factorial design, if we can't simplify it from the whole model, then we're going to be estimating nm different things, one for each combination, and we want to know about variances of those. But if we can simplify it to the additive model, we only need to estimate the values for each main effect. So what should be our criterion? Well, this is the one I tend to use because I have qualitative treatments, and so A optimality is a natural one to me. But a lot of other people here are using quantitative factors, some sort of regression model. But again, are you actually using it for estimating the parameters in there, or are you using it for prediction? And will you be interpolating or extrapolating when you use it for prediction? In breeding experiments, this is going to be plant breeding or animal breeding, typically what you're doing, you've got a large number of new breeds or new varieties, and you do something this year, you select a few of them, carry them forward next year, and go on like that. And what you're aiming for is getting the best so many at the end of the day. What should be our optimality criterion? Are the usual ones like A and D appropriate? And who decides? Should it be the best criterion for humanity, in that we end up with a good variety of wheat for making bread, or should it be a criterion that makes it absolutely clear to the breeders that we've done the fair thing in rejecting something that they've bred? We've heard quite a bit recently about designs for dose escalation, so first in human designs, medical statistics. What would we use as an optimality criterion there? Are we comparing every dose with the placebo? Are we comparing doses with each other? Is what's most important the one you actually settle on compared with the next lower? Or are we actually minimizing risk of toxicity? How do we decide on a suitable optimality criterion for these sorts of experiments? And then, again, when we're thinking about optimality, then there's the whole question of how you optimize. Well, from my background, I'm used to using stuff like algebra or combinatorics and to be able to find something in closed form. But as we've seen even in the talks this morning, many of other people do this through some sort of search algorithm. Well, work done by one of the PhD students at Queen Mary was looking at designs with some amount of symmetry, and he found that if you have a design, if the best design has a very large automorphism group, then it tends not to be close to other locally optimal designs, and search algorithms that move a bit here and a bit there tend not to actually home in on these. So what can we do about search algorithms to make them find designs with so much symmetry? So those are just some ideas of things that I think we need to worry about as we go forward. Thank you, Steve.
Perhaps I could ask all the contributors to come up and open up the audience. So, does anybody have any comments or contributions to make, or questions for any of the speakers? Jeff?
I think in many
Do you
countries in
think
the
we
world,
should try to get the discussants to stand up? Even come
stand
up
up.
on stage?
Okay, yes, if you maybe.
I think it's
There's
very
the
loud. My
microphone.
voice very loud.
The question is whether the people at the back can hear you, isn't it?
You want me to go?
I don't know. You keep talking and see if they put their thumbs up or down.
Okay. In many countries, there's a trend, unfortunate trend. Design community has been isolated from the majority of statistics. Here, we are happy with each other. When you go to any big statistics meeting, design people are isolated. UK may be one exception to a lesser degree because UK has a tradition. I know even some of the leading statisticians who don't know any design from UK, they have some appreciation of design. We go to US, go to younger generation, and John alluded to some of the major stat departments. They don't even offer a course in design. So we need to do our soul search. I think one reason is traditional design analysis are intertwined, but these have been separated. We have a lot of optimal design. We assume one model, then we start doing the mathematics. Anyway, but I think what we need to do, and I have two things. One is we need to go back to do design with more interface with analysis. And the Steinberg gave actually very good. You look at computer experiments, the large number of papers in analysis, because computer experiment is a different nature. Computer experiment, the bigger issues are really, you use a reasonable lighting hypercube, you're fine, basically. But how do you model? Do you do kriging or some other tweaking, or you do numerical? In computation, big issue. So that's an example why it is good. Then the second one is we need to do more applications. And I actually really agree with Dave Steinberg. I think the biggest opportunity, a new one, is in the internet. And this is different, not a traditional design experiment, because internet you have huge data of very complex structure, not a simple graphic. So the design actually is sampling. How do you sample? And I've been to some computer science seminar, and these are leading computer scientists, and they've already done a lot of work, and we are not even aware. So if we don't do anything, they'll take over. But there, I don't think it will be purely the classical design, but we are still the one who know about how to sample data or collect data. So that I think is a big opportunity. Of course, in computer science, you can still do the traditional, the more classical, well, I wouldn't say classical. Design is when you design protocol. But this much less. This happens much less because they wouldn't allow you to change the protocol and run that. But in terms of the massive data and data mining, and so that's one. And then there are others material science. Surprisingly, I don't know why, design experiments should have big impact in material science. And they run experiment, and material take a lot of time and the cost. And we should be able to do that, especially with nanomaterials. That's just some remarks.
Okay, anybody want to say anything in response to that? Can I just, on the very last point, actually, last year there was an international review of mathematics in the UK, and they actually identified material science as an area in which the whole of mathematics was failing to have an impact. So maybe not just design of experiments.
Yeah, well, where we are at Georgia Tech, we work with material scientists in nanomaterial, run experiment, we submit paper to PNS, to material journals. But the other one is computer experiment, is material simulation. I think that one has a tremendous future.
So any other contributions or questions? Please.
actually, I've got two issues. I'm working in a food industry, and to be honest, well, first of all, I need to emphasize that knowing the language of scientists is really, really important, because when they come to us in order to design an experiment, to be honest, we really need to understand what they're talking about. Because actually, at the end, it's us, statisticians, who define their objective, because sometimes they come to us, they don't know what they want, and we start to talk with them and then define their objective, and then based on that objective, we start to design the experiment. But the point is that, as I said, I'm working in the food industry, I'm working with microbiology, with chemists, with agricultural people, with engineers as well. And one of my problems is that sometimes it's really difficult to understand the process. For example, microbiology itself is a huge science. And each, for example, bacterial, well, sorry, I'm using examples, but like Salmonella or E. coli, they're completely doing different, they have different behavior. So I need to understand those behavior first before I can help that scientist. So as I said, because somebody's just mentioned about knowing and understanding the language of the scientists, I just really want to emphasize that we really need to understand that, because otherwise I think we can't design properly, and we can't help them in order to continue their work or their research. The other things is that really, actually, which it hasn't been mentioned here, is about the software developer. We use Minitab, for example, in our company, and sometimes Jump. But what we understood that, people, those who don't have statistic background, yes, those software are good. Minitab is good, Jump is good, and is very good for us as a statistician. But the scientists who don't have that background in statistics, they actually use them, in wrong way, to be honest. I know they are great. They produce wonderful graphs, but when it comes to the analysis, unfortunately, they used it not in the right direction. So I really need, to be honest, in the second issue, I really need help and advice from, experts on how to, how to teach to our scientists that not to, use that software in proper manner, in proper way, rather than misuse those software. Because at the end, when they find the results, it's completely, rubbish.
Anybody in the panel want to say anything?
On your first point, I say a large part of our job is asking really dumb questions. Don't be afraid to look stupid. Say, look, I really don't understand that. You may think I ought to know the technical term, but I don't. And quite often just getting them to explain it over and over again will bring out some of the issues that they haven't thought about themselves. And the second one on using the software, something I find a lot these days, if I'm advising, say, postdocs or PhD students from another department, I've got my laptop, and this laptop has on it this wonderful piece of statistical software that I've never heard of. And, I'm going to use that. I say, look, please don't, because I have no idea about that software. I don't know whether it's doing the right thing. If you do it in Minitab, and you then show me what you've done, I'll be able to give you some advice on whether that's right or not. So I try to encourage people to use the standard things so that we can easily see whether they've done it right or not.
Thank you.
Oh, that's us.
I just want to make a very quick comment with regard to the communication with scientists. Our main communication as a community, and here not just the design of experiments community, but the statistical community with scientists, is the large body of courses which I think all of us who are involved in university education teach. Introduction to statistics for this group and that group and that group. And if you give at least meetings that I've had with these people afterwards, on occasions where I've been asked to teach them something about design of experiments, almost everyone who's gone through these introductory courses, when I ask them, what did you learn about the design of experiments, I get an absolute blank. And I think one of the opportunities, the missed opportunities that we've had, is incorporating more issues of what makes for good data, usable data, quality data, and how that links to the kind of data that you should collect and how you should design your studies and experiments in those introductory courses. We failed miserably in that, and it's an area where we can improve considerably.
Okay, thanks. Henry?
So this is the Isaac Newton Institute, so maybe we should widen the scope of experimental design a little bit. So sensor location has been mentioned as one of the areas, and indeed, if I look towards the panel, I'm collecting information from this end of the room as opposed to that end of the room. And there's a lot of paradigms. If I do transept sampling in a forest, I'm marking trees as I go along, I'm collecting data on a transept. So there's lots of paradigms out there. Computer vision, supervised learning in machine learning, where people are collecting data in special ways. And we should really open up experimental design to those more general areas of data collection, maybe sensor location, but you can have moving sensors. You know, you can collect data in innumerable different ways, not just control experimental design of the sort which we're largely talking about this.
And Ben?
On Anthony's point about minimal support designs, I've always thought that you could consider a mixture of designs, which each of those being centered on these minimal support points, which would give you the opportunity to test the model, but maybe be near optimal if you have found the correct design.
Mm. Yes, well, Rosemary also, of course, mentioned the business of having more than one model. And indeed, if the models are, particularly if they're non-linear, then it's really is quite a tricky problem, I think, that we seem not to have addressed very much over the last 40 or 50 years.
Dennis?
Apart from all the wonderful comment, I think I just want to be a brief one. I think if you think design experiments basically how to collect data efficiently, we need to extend the idea about data. It's not numbers, but you don't give a wonderful talk about facial or something like YouTube data, like video, whatever. Those are all design experiment problems up behind that, but we don't know what data are all about. We need to extend the idea about what do you mean by data. Image is data, voice is data, motion is data, YouTube or whatever, even Google, there's all kind of data there, and we don't treat them as data somehow. And therefore designs will never come in somehow on those areas. Those are one point I think you think. And I really like the comment about we need to keep up with new technology. There's lots of new thing there, and we somehow will close the door hiding. I think this program has been wonderful to me because I realized after 4 weeks that I really don't know much about design. It's good news for me. Our final comment was I think design is difficult for mathematics because they never run experiment, not even design experiment. They don't run experiment. For those places that collect data run experiment, design experiment make a whole lot more sense. For those people who got given x1 to xn, there's nothing about design. They have nothing about experiment. So that's the point I talked to Bill Hunters, but not Stu Hunter some years ago about this. We teach in different area that they never run experiment. What do you mean by design experiment?
Brad, you wanted to say something?
I was just going to say that in terms of thinking about computation and software and how it relates to all of this is that the grand plan in JUMP is to connect all of the analytical tools with design tools so that design always leads to analysis in a natural way. Typically, books on design of experiments spend more time talking about the analysis of experiments than the design of experiments, and only consider very limited kinds of analyses, just least squares kinds of stuff. But if you have connection between design and analysis for every analysis type that you're thinking of, then you have a natural way of perhaps guiding people to think in terms of using design when they're thinking about analysis. So it's a future a goal anyway.
Hey, Debian, you wanted to?
So I think the thing that concerns me most in this discussion today is, I don't know what's the right word, but a little bit of alienation from the rest of the statistical community. I mean, we seem to be somewhere on an island all by ourselves, and I'm wondering how did that happen? It didn't happen overnight, though. I mean, I have been, for instance, when the annals of mathematical statistics split into annals of statistics and annals of probability, I've been talking to people about the birth of JSPI, and I was told that at that point people were saying, where will the design folks be? Would they be in the annals of statistics? Well, they cannot be in the annals of probability. Will they be annals of statistics? Well, not really, because they are too mathematical. I mean, there was a group of people who thought that way. Fortunately, we were still able to publish in the annals of statistics. But what I'm wondering, I would like to know what you think. Why did it happen this way? As Brad says, I mean, there are tools. There are computation tools, there are analytic tools, there are software. But why is it that the things that we do have not been incorporated in textbooks, the first-year courses, like David says, or by the community? If we cannot sell the statistics community our own work, how can we go beyond?
Do you have any comments on that? Shall we take one last question or comment?
Yeah, I just wanted to comment about the need for flexibility in graduate programs. And I can speak most knowledgeably about U.S. programs where many programs require at least 2 years worth of training in what's called core subjects. But, you know, the core we're talking about here, I think requires, especially if you're going to be on that rim, a different kind of flexibility and training than the core if you're right at the hub, let's say. And I think programs are a bit calcified in terms of what they think of as cores, and there has to be, maybe in the new generation that's coming up, not in the people that are in the 55 to 65-year-old age bracket, recognition of the importance of computation, interaction with scientists, and the fact that, you know, perhaps a different kind of training is needed if one is thinking about a 30-year career and is going to be graduating in 2015, let's say, than what was needed in 1975. So, and that's a struggle I think many departments in the U.S. are dealing with, perhaps less so here in the U.K. It'd be interesting to hear about comments about what's happening on the continent with respect to training and the flexibility that's allowed.
Does anybody want to comment on that?
I want to make a comment on the previous thing actually about education. I think we all have to look to Doug Montgomery really to solve this problem.
Oh no.
Doug does often write books on both elementary statistics and on the design of experiments. I have taught from one of your engineering statistics books. You have stuff on regression. Perhaps you should then have, you know, the moment after we introduce this, you should say, is this the best possible choice of the values of X? Whenever these things, I mean, this is just an idea that if you want to, other people could do this, of course, as well. But you get the idea.
But I'm available.
and revising all the time. So you tell me. So you know, if you want to get the idea of the design of experiments in there at the very beginning of statistics, then perhaps all the time you need to say, you know, why were these levels chosen? Why these particular value of X? Why this value of N? Is this all sensible? I don't. This might. This is of course I'm off the top of my head. And so anyway.
Good point.
Thank you. Okay. So get writing.
Sue, you wanted to say something?
I know I shouldn't, because it's past the last question. But just to be a simple observation, really, into the discussion around the barriers that we actually have to overcome for people, whether they be scientists or people you're trying to advise in industry, for them to actually appreciate what design of experiments can do for them. Somehow they have to try without designing an experiment scientifically and see it's not good enough. And of course, in real life, that's a very difficult thing to do. And the way I've seen that works quite well and is now incorporated for our Master of Chemistry students at Southampton is to give them in that case, a simulation of a real chemical process with a model behind it, and you ask the chemist to optimize the yield from this reaction. And of course, they work in groups and spend a long time using their chemistry knowledge to say what combinations of the various chemicals should be made to produce this. And these ideas actually came in to us from the pharma industry. And they then they take an enormous amount of runs to actually get to where they think is good. And then, of course, you can show them then that with far fewer runs using structured experiments, they can reach their objective so much more efficiently. And that, you can almost hear the penny dropping when they see that. And I think we kind of have this problem, whatever level you're dealing at, they don't understand the gain somehow that they can make from proper design of experiments.
Okay, well, I think we best wrap up. I hope we can, some of us at least, can continue the discussion over coffee, tea, lunch, whatever. So let's thank the panelists again, please.